Section 4.3, how derivatives affect the shape of a graph. All these are just applications to derivatives. So what are the things we're going to be covering in this section? What is the first thing we're going to be covering? First thing is we are going to talk about when is the graph increasing and decreasing. So the first point is increasing, decreasing. Using calculus or derivatives. The second one, we're going to introduce what we call first derivative test. First derivative test. And then we're going to talk about concavity and concavity test. What is concavity and how is it used for when it comes to graphing functions? Then point or points of inflection. Then we're going to talk about the second, what we call the second derivative test. Second derivative test. And then how we apply all of this to graphing functions or graphing derivatives, or how the derivative affects the graph here. All this we'll put in one problem and see how we apply it. So to start with this one, let's start by writing down, drawing a graph, any graph of any function. Let's say I'm going to graph this. Okay, that's the graph of f. If someone wants to draw a tangent line, just draw a tangent line here at some point, at this point. If I draw a tangent line at this point, it would be like this. I want to draw another tangent line like that. At this point, it would be like a horizontal tangent line. And then as you go up, it's going this way, another one. And at some point you have a horizontal one, and then another one here, another one here, another one here. So notice something here, based on these tangent lines that I drew, the first like 2 or 3 of them, it shows that the line is going down. So they have a negative slope. They have a negative slope. And remember, derivatives at that point is really the slope of the tangent line. So this tells us if the derivative less than 0 means has a tangent line that is with a negative slope on, let's say, an interval, let's call it I, it's not just at a point, then f is decreasing on I. Same thing happened we notice when the graph goes up, which we call increasing, it has a positive slope. So we say if f prime of x bigger than 0 on I, means on the interval I, then this means f is increasing on I. Okay, and we know when it's a horizontal tangent, the derivative is 0. So let's see how we apply this here. So we would like to determine where the function y equals f of x equals 2x cubed minus 9x squared plus 12x minus 5 is increasing. I'm gonna put an arrow for increasing. And where f is decreasing like so. So how are we gonna use what we learned to figure out this? Well, the first thing is we find the derivative, because in order to test what is it decreasing and increasing, we need to find the derivative of the function. So y prime is 6x squared minus 18x plus 12. One thing I see right away is factor the 6 out. So that gives us x squared minus 3x plus 2. So y prime equals 6 times x minus 2 times x minus 1. It's factorable, so it's easy. So I would like to know or test when is this positive and when is it negative. Because that's what they're asking us. Basically find the interval, where is this function increasing and where is it decreasing. So I'm gonna draw a number line that would help me figure out where is this function increasing and where is it decreasing. The points that we put on the number line. Here I got 1 and 2. 1 and 2. So if I pick what we call a testing point, say x equals 3, and substitute it in here, what we get? We're going to get a positive value. So this interval is positive. Pick like 1.5, you're going to get negative, then positive. So what is this saying? F prime is positive for x less than 1 and x bigger than 2. That's when the function is going to be increasing over these two intervals. So you can say, in other words, it's from negative infinity to 1, union 2 to infinity. Now f prime is decreasing or less than 0 for x between 1 and 2. That's when it's decreasing. Notice we don't put or equal, just in between 1 and 2. 1 and 2. So that tells us when the function is increasing and when is it decreasing. So the question is asked, why do I need to know this? The idea behind this is we are trying to learn as many information about the use of derivatives to get to the point where we would be able to use them to graph more complicated functions by hand without using calculators. So that's the idea behind this. That's one applications, of course. So let's do the same thing with a more complicated function. Say x squared minus 1 to the 2/3. So what are we going to do here? We're going to find y prime, bring the 2/3 down, x squared minus 1 subtract 1 times the derivative of the inside. So y prime equals 4x over 3 times x squared minus 1 to the 1/3. So that gives me this function, its derivative. Now what goes on the number line? Do I just put what makes this 0 on the number line is 0, x equals 0. So 0 goes on the number line, that's one of the values. What other values can go on the number line? What makes the y prime undefined? So what makes the denominator 0? Positive and negative 1. So basically what I'm putting on the number line, those are the critical numbers. Those are the critical numbers. If you remember from 2 sections back, from section 4.1, critical numbers. So critical numbers can be found by setting the derivative 0 or does not exist. So there are 3 values here. Now we're going to pick some testing points, say x equals 2. So if you substitute in, you don't have to get the exact value. You just know that the denominator will be positive and the numerator positive. So this will be positive the whole time. If you pick 1/2, the top will be positive, but the denominator will be like 1/4 minus 1. That's a negative. If you pick negative 1/2, the top will be negative and the bottom negative. That will become positive. If you pick negative 2, the top negative, the bottom positive. So that's negative. So as you can see here, it's going down, up, down, up. So down means decreasing, up means increasing. So the function eventually will end up to be increasing over the interval negative 1 to 0, union 1 to infinity, and decreasing on the other intervals from negative infinity to negative 1, union 0 to 1. That's what how we test where the function is increasing and where is it decreasing. So now in connection with this, we introduce what we call the first derivative test. First derivative test. First derivative test said we suppose that C is a critical number. Critical number of a continuous function f if f prime, if f prime changes from positive to negative, then f has a local maximum at x equals c. And I'll explain what that means from positive to negative. B, if it changes from negative to positive, then f has a local minimum at x equals c. Next, if there's no change in the sign, then f has no local min or max at x equals c. So if you want to really kind of like memorize it, easy way to memorize this, think about the number line. This is a number line. Just pick any 2 points, A and B, and say, you remember how we did the previous example, positive, negative, positive, or something. Let's say it this way. It doesn't matter, positive, positive, or negative, positive, negative. So this is going up, increasing, decreasing, and increasing. So let's go back to what this test is saying. It says if the sign is changing from positive to negative, and as you can see here, it's changing from positive to negative, right? Positive to negative. This means if positive to negative, there is a maximum here. You see how it went up and down? There's a local max at x equals a. Notice what happened next. It changed from negative to positive. So the test said part B changes from negative to positive. F has a local min, and you can see that here. So there's a local min at x equals b. Local min at x equals b. This is the easy way to memorize this one. So let's see how we apply it. Find the local extrema. Extrema means min or max, min and max or max. For, let's say y equals f of x equals x to the fourth minus 4x cubed. Let's look at this function. So what do we need to do? Well, to see which one is local min, which local max, we need to find the critical numbers first. So to find the critical numbers, we find the derivative and set it equals 0 and or does not exist. So that's 4x cubed minus 12x squared. You can factor out 4x squared, so that will leave x minus 3. So what goes on the number line? We see 0 is one of them and 3 is the other one. Testing points as before. So let's say I'm going to pick x equals 4. Substitute in. That will give me positive. All of them. If I pick 2, let's say I pick 2, that will give me negative. If I pick a negative one, that will also be negative. So it's going down, down, and up. So notice that change in the sign. Negative to negative, like at 0, there's no... so at x equals 0, there is no local min or local max. Min or local max. Okay, at 0. What about at x equals 3? At x equals 3, the change is from negative to positive. Well, let's see. Negative to positive by the test. It's b. So there's local min. And you can see it. It's a local min. So there is a local min at x equals 3 by the first derivative test. First derivative test. What about looking at a more complicated one? Say y equals f of x equals x to the 2/3 times x minus 5. So the first thing we do is we need to find the critical number so we can use the number line. So how do we use the critical number to use the number line? So first we need to find the derivative for this. Y prime by the product rule. Bring that down first. X to the negative 1/3. X minus 5. Keep the first one the same. The derivative to the second one is simply 1. And now what we need to do is bring that down. 2 times x minus 5 stays up there. We don't like to see negative exponents, so you bring it down. The other one stays the same. Now I need to combine the fractions by multiplying here by the common denominator, which is 3 times x to the 1/3. And eventually in all these cases, that will give us a simpler numerator with no rational exponents. Let's see what we get. 2x minus 10 plus 3x. So that makes it y prime equals 5x minus 10 over 3x to the 1/3. So that's what we get for the derivative. Now, what makes this 0 and or does not exist? So 0 is one of them and 2 is the other one. So what do we got here? We got to test, let's say x equals 3. If I pick x equals 3, substitute it in here. Not in the original function, always in the derivative. So this is the line for derivatives. We're checking where is derivative positive, negative. So if you substitute the 3 and you're going to get 15 minus 10, that's a positive. And the denominator positive, so that's positive. 0 to 2, pick 1. 1 will give us negative on the top, positive in the denominator, so negative. And the bottom one may be negative 1. That will give me negative on the top, negative on the bottom. That's positive. Keep in mind, it's not always alternating positive, negative, or negative, positive. Sometimes you can have a case like the one I showed you in the earlier example. This one, it was negative, negative, positive. So that's something you have to watch for. Now, by the first derivative test, we see there's a change from positive to negative in the first one. So there's a local max at x equals 0. And there's negative to positive, there's a local min at x equals 2 from negative to positive. Now we introduce concavity and the concavity test. So first, what is concavity? Let's say I have a graph like this. Notice we graph from left to right. I see the graph is opening up. As you can see, this is opening up to maybe this point, let's say. Up to this point. Then it starts opening down. So in the first half on the left, this is opening up, so it concaves up. The graph, we say the graph concaves up. And here it concaves down. There's a point here, I'm going to call it I. Or, yes, we usually call it I, but let me change it to T, for example, for now. Because I'm going to call the interval I. So, the graph concaves up at some point or over a certain interval and then concaves down on another interval. The concavity test, we have concavity test. It states if the second derivative bigger than 0 for all x in an interval I, then the graph of the function f concaves upward on I. That's what it is. Now, if the second derivative, so the test said if the second derivative is less than 0 for all x in I, then the graph of f concaves downward on I. That's what concavity test said. So over this interval here, from here on, that's when the second derivative of x bigger than 0. And over this, from here on, that's when the second derivative is less than 0. So the concavity test tells us when does the function or the graph of the function concave up and when does it concave down. Now that point t that I put here, I labeled up there. That point t is called inflection point. That's when the graph changes its concavity from up down or down up. It's called inflection point, or some people call point of inflection. Point of inflection. Let's try to apply to an example here. Determine where f of x, say x cubed minus 6x squared plus 9x plus 30 is, or where this concaves up and down. So let's see when this function concaves up and down. Notice by the concavity test, it's talking about the second derivative. So it would be nice to find the first derivative, which is 3x squared minus 12x plus 9, and the second derivative here is 6x minus 12. So when is this bigger than 0? It's bigger than 0, the second derivative bigger than 0, when 6x minus 12 bigger than 0. So when 6x bigger than 12, when x bigger than 2. So the graph is going to concave. So the graph, we say the graph of f concaves up over the interval 2 to infinity. The same thing is going to happen for the second derivative. Is less than 0 when 6x minus 12 less than 0. So x less than 2. So we say the graph of f concaves down over the interval negative infinity to 2. Negative infinity to 2. So at that point, note, at x equal 2, f has point of inflection. Point of inflection. Point of inflection. So we can say, we can introduce this as a definition. If the derivative at c is 0, then the point c comma f of c is called point of inflection. As stated above. And this is followed by a theorem. The theorem said, if the point c f of c is an inflection point, it's an inflection point, then either the second derivative at c is 0 or the second derivative at c does not exist. It's kind of similar to the first, when we did the first derivative work. So let's look at an example on this. Find point or points of inflection for y equals f of x equals x to the 5/3. How do we find points or points of inflection? So we find f prime of x is 5/3 x to the 2/3. And that's the first derivative. Second derivative, we keep the 5/3 out as a constant, bring the 2/3 down, subtract 1. So that will give us, if we simplify this, bring that down because negative, So 9 to x to the 1/3. Notice this will never be 0. So does that mean there's no inflection point? Well, what about the derivative, the second derivative does not exist? When is it does not exist? That occurs when the denominator is 0, means that x equals 0. So we can say that 0, and if you substitute back into the original to get the y value, 0 again is a possible point of inflection for the given graph or for the given function. Now, how do we exactly confirm that this is really a point of inflection? And that's what I wrote here. I wrote a possible point of inflection. How do we confirm this? Of course, by the theorem that we stated, that is confirmed there. But let's see, we use the concavity test. Concavity test to check if really 0, 0 is an inflection point or point of inflection. So based on if you look at the second derivative again, it was 10 over 9x to the 1/3. Notice when x is less than 0, the second derivative is less than 0. So the function concaves downward. When x bigger than 0 means the second derivative is bigger than 0, the function concaves up. So what does that mean? It looks like this now. Say this is the number line, this is 0. So it concaves down here and it concaves up here. So this point t, which is 0, 0, is an inflection point. See how the concavity test confirms this? Now let's take a look at another example. Y equals f of x equals x over x squared plus 1. Let's start by finding the first derivative, y prime. Y prime, by the quotient rule, we have the denominator times the derivative of the top minus the derivative of the denominator times the top one. So y prime equals, this is x squared plus 1 times 1 minus 2x times x all over x squared plus 1 squared. What do we get for this? Y prime equals, this is x squared plus 1 minus 2x squared over x squared plus 1 squared, which equals 1 minus x squared over x squared plus 1 all squared. That's what we got for the first derivative. Now, this, from here we can find what we call critical numbers. I'm going to put those on the number line. If we solve this equal to 0, we get x equals 1 or negative 1. So I have 2 points, negative 1 and 1. Infinity, negative infinity on the number line. I'm going to test the first derivative. Remember, this is the number line for the first derivative, not the function, not the second derivative. So when I pick testing points, I pick a value here, say x equals 2, and I substitute into y prime or f prime, not to the original function. So if I substitute the 2 in here, I'm going to get 1 minus 4, that's a negative. Notice the denominator is always going to be positive. If you pick something here, say x equals 0, that's going to give us positive. Pick something here, x equals negative 1, that's going to give us negative. Negative 2. That's going to give us negative. So notice here, it's negative means decreasing, increasing, decreasing. So we say f, one thing to get out of this, f is increasing over the interval negative 1 to 1. F is decreasing over the interval negative infinity to negative 1, union 1 to infinity. That's what we have about increasing, decreasing. Another thing we can get out of this, f has a local min local min at x equals -1. And if you like to find the exact point, you can substitute this into the original function to find the corresponding y value, which I already did, and I got a -1/2. F has a local maximum, so I'm putting everything we learned into this question, at x equals 1. And again, if you substitute this back into the original function, you're going to get 1/2. And these things, I saw them on the number line, how there's a local min here at this point, and there's a local max at this point. But it's confirmed by the first derivative test. So you can say by first derivative test. That's what this is. So from the first derivative, I'm gonna move on to concavity. So from f prime that we found earlier, or y prime, it was 1 minus x squared over x squared plus 1 squared. So if I find the second derivative, by the quotient rule again, I'm gonna let you try, but you're gonna get 2x times x squared minus 3 over x squared plus 1 to the third power. Notice the denominator is going to be always positive here because of the x squared plus 1 is always positive. So what goes on the number line to check for second derivative? I see if I set the top equals 0, I got 0, one of them. And from the x squared minus 3 equals 0, x squared is 3, x is plus or minus. Don't forget the plus or minus. So let's say that's here and the other one on the other side. Negative infinity, infinity. Now I'm testing the second derivative. Not the first derivative, the second derivative. And to do so, what we need to do is we need to pick a value here for x. Say x equals 2. Say x equals 2. Because square root of 3 is 1.7, about 1.7. So if you substitute into the second derivative, not the first derivative, not the original function, second derivative, that's going to give us 4 minus 3, positive, positive. So everything is positive. And then if you run, let's say you choose x equals 1, that will give us negative. -1. That will make it negative by negative, positive. And then negative. So notice it's down, up, down, up. So notice this is the second derivative. This is not increasing or decreasing. So this tells us the graph of f, concaves. First up over negative square root of 3 to 0, union square root of 3 to infinity. And down over negative infinity to negative square root of 3, union 0 to the square root of 3. So I was able to get the concavity thing. Now what happened to these 3 points that we see here? These are points of inflection. That's where the graph changes concavity from down to up, up to down. And if you like to find their corresponding y value, so if I take x equals negative square root of 3, to find the y, you substitute into the original function, which was x over x squared plus 1. That will give us negative square root of 3 over 4. So one of the points is negative square root of 3 comma negative square root of 3 over 4. Next point, if x is 0, that will give us 0 over 0 squared plus 1, which is 0. So another point is 0, 0. And we do the same thing for the last one. X equals square root of 3, y equals square root of 3 over square root of 3 squared plus 1. That's square root of 3 over 4. So the third inflection point is square root of 3 comma square root of 3 over 4. So that gives us a good idea. So what we did here, we basically discussed the given function or curve with respect to concavity, point of inflection, local min, local max, was it increasing, decreasing? All this was applied to this one. We can take a look at another example on this. And take a look at another example. Discuss concavity and points of inflection. For the graph of y equals f of x 3x to the 1/3 plus 2x. Students find this kind of questions a little bit more difficult than just polynomials because this has rational exponents. So it makes it more difficult to work when it comes to finding derivatives of such functions. So let's see what we have here. First thing, we find the derivative, which is keep the 3 out, 1/3 down, x to the negative 2/3 plus 2. So y prime equals x to the negative 2/3 plus 2 after simplifying. We need to find the second derivative. Then we find y double prime negative 2/3 x to the negative 5/3 plus 0. Again, we don't like to see negative exponents in the answer. We have to bring it down like so, plus 0. Well, to find what we need to put on the number line, the critical points, critical numbers. Where is this equal 0? Never. When is the second derivative does not exist? When the denominator 0, means when x equals 0. So then negative into infinity, 0 goes in here. So if you pick a testing point, x equals 1. Remember, what is this? I'm testing the second derivative. So when I pick a testing point, x equals 1, I substitute that into the second derivative. I substitute in here. That will give us a negative. If I pick x equals negative 1, that will give me negative on the top, negative on the bottom. That's a positive. So this tells us the graph concaves up from negative infinity to 0 and concaves down from 0 to infinity. So here we have when x is 0, substitute into the original graph or original function, you're going to get 0 plus 0, 0. So this point 0, 0, where the graph changes concavity, is an inflection point. That's an inflection point. So far we introduced first derivative test. We went through when is the function increasing, decreasing. We introduced concavity test, inflection point, and how we find them within one function. Now remember, the whole section is about how derivatives affects the graph of a function. And we notice increasing, decreasing is one of them. Concavity is another one that helps us to get a better graph or more accurate graph when we sketch graphs of a given function by hand. That's how these help us. Now, what about if I look at they give us, let's look at this one. What about if they give us y equals, let's say, the graph of x squared. This is f of x. Okay, so I'm gonna graph this function here, which each one of you already know how to graph it. It's the parabola that goes through the origin like so. Now, if I find its derivative, what do I get? 2x, right? So how is the graph gonna look like? X 0, 0, so it's gonna go like this. X 0, y. If I find the second derivative for this, which is gonna be 2, how the graph is gonna look like? Y equals 2. Think about this way, right? So each one of them, y prime equal to x, that's a new function. That's y equals something as a new function. So what happened here is, this is just the function. It's the graph of the function, the graph of the first derivative, and the graph of the second derivative. So what happened here is, basically I have what I call some guidelines to help the students graph a function or the derivative of the function, or vice versa, without even having the function itself. So here I was able to graph the derivative because I knew what the equation of the function was. But if I didn't know it, so how, if they give me just this parabola, how would I graph that slanted line in the middle of the screen. Or if they give me that slanted line, how do I graph its derivative, which is that horizontal line, without actually finding the derivative of them? Because I don't know, I'm not going to know their equations. Well, these are some guidelines. So the first guideline, let me put it this way. If the function has either like a point here, it's kind of like min or max, either min or max, then what happens for the derivative, that min or max is gonna go down on the x-axis. Min or max is gonna become on the x-axis, and I will explain in a minute what that means. So if you see min or max on any function or graph, we bring it down or up on the x-axis. So that point, those points that I bolded here, those are gonna be on the x-axis. Okay. Now, if you remember, this function is going down, right? It's decreasing. It's going down. So it's going down means it's decreasing. So when the function is decreasing, what happened to the graph of its derivative? Well, when it's decreasing means f prime is less than 0, right? It's less than 0. So what does that mean? Means the graph will fall below the x-axis. Below the x-axis. That's what less than 0, because 0 means the x-axis. So this 0 that I put here, that's the x-axis. What about if it's increasing? Well, the other way around. So if it's increasing, then this means that's when the derivative bigger than 0. So the graph of the derivative will fall above the x-axis. Above the x-axis. That's what this is. So let's look at this graph, the one that I just drew. Notice what happened. First thing, the graph was going down here, right? It's decreasing. So the first section of it on the left is decreasing. So the graph of f is decreasing. The graph of the derivative should fall below the x-axis, which matches here. Do you see it's below the x-axis? The x equals 0 point, you know, that's minimum. It became on the x-axis, which stayed as is. And for the next part where the function is increasing, what happened? The graph falls above the x-axis. That's what these three guidelines, they help us a lot to graph functions, I mean the derivative of a function without actually knowing what the equation of the function is. So let's look at another graph. So I'm going to look at a graph. I don't know its function. I don't know its equation. So let's say it goes this way and then up. I don't know its equation. I just know it's f. I label x, y, the origin, the function. So I'm going to graph. So sketch a graph for its derivative. Sketch a graph for its derivative. So how are we going to graph the derivative of this function? So the first thing I'm going to label is this point here, point A, and point B. Those are like kind of min and max. We call them local min, local max. Those are going to go down on the x-axis. So down or up. So let me redraw this, the xy plane, y. So if I draw a horizontal line down the paper like this all the way, so that point A becomes here on the x-axis. Point B, if you project it down, it's gonna become here. Do you see A here and B there? So they are gonna become on the x-axis. Now let's start from the left side, the left of point A. The function or the graph of the function, this part here, it's increasing. So this means the graph of the derivative, see look, if it's increasing, the last row, the graph of the derivative should fall above the x-axis. So they should be above the x-axis. Now when it falls above the x-axis, there are two ways. So I'm going to show you both cases. This way, that's above the x-axis, or this way. Okay, or this way. Notice the difference. What's the difference between these two cases? And it's good to know both of them. The difference is that in the first one, it was concaving down. In this one that I still have on the screen, it's concaving up. Concaving up. But let's see which one is going to work. Let's keep this for now. Okay, let's keep this for now. So now, what's the next one? What's the next one is what happened in between, you know, in between point A and B. It's going down. Do you see it? It's going down. It's decreasing. So when it's decreasing, the graph must fall below the x-axis. So it's going to go this way, and then it's going to reach B at some point. Now, some people might bring it more down. That's okay. We are sketching graph. We're not graphing a function like a perfect graph. It's just a sketch. Now, from B on, it's increasing. Increasing, the graph of the derivative should fall above the x-axis. So this would be the graph of the derivative of the function. See, with no calculator, without knowing what the function exactly is. That's a good example. Now, is there any other, can they ask us in a different way to graph functions or sketch something related to this? Well, let's look at another one, but no graphs given. Sketch the graph of a function f, having the indicated characteristics. What are the things given? F of 0 equals f of 3 equals 0. F prime of x less than 0 if x less than 1. F prime of 1 is 0. F prime of x bigger than 0 if x bigger than 1. The second derivative of x bigger than 0. This means for all x. So all these are conditions or characteristics on f. We need to put all of them together to get a graph for the function f. So let's start with this one at a time. F of 0 equals f of 3 equals 0. What does that mean? It means when x is 0, y 0. When x is 3, y is 0. So that means we get 2 points from here, 0, 0 and x3, y 0. So 2 points. So let's plot these 2 points, 0, 0 and 3, 0. 0, 0 and 3, 0. So the first point goes here, 1, 2, and 3. These 2 points. F prime of x less than 0. What does this mean? What does this tell me? This tells me, hey, the graph is decreasing. Is decreasing when x less than 1. So this is 1. So anything to the left of 1 is going to be decreasing. And remember, the graph must go through the origin. So decreasing, again, it could mean like this, or it could mean like this. Either concaves up or concaves down. Let's see if they give us something about concavity. Oh, the last condition. The last condition tells us that the function concaves up for all x. Concaves up. So this means it's not going to be this one. It's going to be the other one. So let me redraw it again from scratch. So it's going to be this one, not the other one. So the function is going to come down, decreasing anything to x equals 1. It's decreasing and it concaves up. Next one, so I'm done with the first condition. I used this, the points and this. F prime at 1 is 0. What does that mean? It means at x equals 1, there's a horizontal tangent. That's what this means. But notice, so this is done. Notice it also must go through this point, 3, 0. So how am I going to make it go through that point? So then you have to, let's erase it and then do it again. The same one, but we keep erasing and putting it together to get really a good graph. So you're not going to get it right away by just looking at it. So it's going to go through this. At some point, I'm gonna bring this down. So concaves up is gonna go through this point, and let's see, it's gonna go through that point. Let's see what happens after 1. So it says it's increasing to the right of 1 when x bigger than 1. So to the right of 1, do you see how it's increasing? Also, they're saying it concaves up. Notice, let's check all the conditions. There's a horizontal tangent at x equals 1. It goes through 0, 0, 3, 0. Concaves up all the time. Decreasing when x less than 1. Increasing when x bigger than 1. So it satisfies all these characteristics that they give us in the problem. Now, as a final thing here in this section, is we introduce what we call the second derivative test. Since we started with the first derivative and we called it first, this means you expect to see a second derivative test. So the question, what is the second derivative test? You know, what is it and how do we apply it? So the second derivative test said assume that f prime, which is the first derivative of the function, is continuous at x equals c. And the test said if f prime at c is 0, means it's a critical number, and the second derivative at that point is bigger than 0, then f has a local min at x equals c. Same thing, if the first derivative at c equals 0 and the second derivative at c is less than 0, then f has a local max at x equals c. That's what the second derivative test said. Now, how do we apply it? It helps us to find minimum and maximum, local min, local max. Let's look at an example. Find the relative extrema, min and max, for the function y equals f of x equals negative 3x to the 5th plus 5x cubed. To do so, because if I want to apply the second derivative test, I need to find the c values first. So those are basically the critical numbers. So we find y prime, which is negative 15x to the 4th plus 15x squared, and set it equal to 0. If you factor or divide everything by negative 15, that will give us x to the 4th minus x squared equals to 0. Factor x squared out, so that gives us x squared minus 1 equals 0. Then x squared times x minus 1, x plus 1 equals to 0. So what values of x we get? X equals 0, 1, and negative 1. 3 values. So those are the c values. Those are the critical numbers. Then we need to find, so we found the c, we found those. So these things help us to find the c values. Now we're going to test if the second derivative at c is bigger than 0 or less than 0. And then students may ask, what about if I tested and I got 0, like the second derivative at that point is 0? Then in this case, the second derivative test does not tell us anything. Like we say, the test fails to work in that case. So we need to evaluate the second derivative at c. So let's see how we evaluate this. We do need to have the second derivative. So let's find the second derivative, which is negative 60x to the 3rd plus 30x. Okay, I don't have to solve for x values here anymore. I don't have to. I can just keep it as is. Or sometimes some people factor 30x out. They find it's easier to calculate this way, but it's not necessary. So at the first point, when x is 0, okay, when x is 0, if I substitute, so we continue with this question that we started with earlier to find the relative extrema for this function. We found the first derivative and the second derivative. And I'm trying to use the what we call the second derivative test. Okay, so f prime of c equals 0 helped me to find the critical numbers, and in this example there were 0, negative 1, 1, and then I'm substituting the second derivative for x equals c. So I'm going to evaluate when x is 0. If we substitute this back into the original function, you get 0, 0. And at that point, what we have, at that point, the second derivative, if you substitute into this line right above it, that's going to be 0. So in this case, the second derivative test, the test fails to work. So the test fails to work. If I do at x equals 1, the point would be 1 comma, substitute into the original function, the blue one, negative 3 plus 5. So that's a 2. So the second derivative at x equals 1, what do we get? If you substitute in, you're going to get negative 60 plus 30. That's negative 30, less than 0. So the second derivative test tells us that there is a local maximum at the point 1 comma 2. And the last point, x equals negative 1. So if you substitute that into the original function, we get x equals negative 1 and negative 2. So if you evaluate the second derivative at negative 1, that would be positive 60 minus 30. So that's 30, bigger than 0. So there's a local min at negative 1, negative 2. So as a note, let me add one note here. Since the second derivative test failed to work at 0, 0, we can use, just in case you say, what am I going to do at 0, 0, or what's happening at 0, 0, we can use the first derivative test. To check if there's a local min or max at that one. Just keep that in mind.